So let's continue with the modeling of the electrical machine. And last time we found a method to calculate the torque or the force from the field energy or the co-energy. And simply, if we're discussing a rotation type system, we say that the torque will equal partial omega c by partial theta when the current is constant. And if I'm using the field energy, then the torque can be calculated as minus partial omega f by partial theta when the flux linkage kept constant. And we stated that the inductance is very important for the electrical machine. Without a varying inductance with respect to the rotor position, we cannot generate, let's say, a torque or self-reluctance torque. If I need to generate a torque, I need more excitation. And we discuss how to calculate the field energy for the single excitation and for the multiple excitation system. Now, briefly here, we are interested in the inductance in the machine. Now, in general, if I'm discussing a rotating type system, I will have stator and I will have a rotor. Now, for the stator, we have a self-inductance, which in general we call it LS, and also we have a mutual inductance. With a mutual inductance between the stator and the rotor, so we call it MSR, let's say, the mutual inductance between the stator and the rotor. The same thing for the rotor. We will have the self-inductance, which is the LR, and the mutual inductance, which is the MRS. And if we need to calculate any self-inductance, then, for example, if I need to calculate LS, then, and I'm assuming a linear magnetic circuit, and we know that for linear magnetic circuit, let's write it here. Lambda can be written as Li. So simply, if I have the flux linkage, and if I know the current, then I can calculate the inductance by dividing the flux linkage over the current, which means that if I'm excite the stator winding, then I can have a method to calculate or measure the stator flux. Then the self-inductance of the stator will equal lambda s over Is. The same thing here. If I excite, let's say, the rotor by a current IR, and if I can calculate lambda R, then LR will equal lambda R over IR. Now for the the mutual inductance, I'm having two options there, because MSR is equal to MRS. The mutual inductance between the stator and the rotor is equal to the mutual inductance between the rotor and the stator. So in general, I'm having the MSR is equal to MRS. So if this is the case, I can measure or I can calculate the mutual inductance in two ways. The first one, for example, if I excite, if we excite the stator by IS and calculate or measure let's say measure the flux linkage lambda R and calculate the flux linkage in the rotor. Then MSR will equal lambda R over IS. So this is the first option. The second option, simply I will excite the rotor by a current IR and find lambda S. So the same thing, I can find the mutual inductance between the stator and the rotor by lambda S over IR. So simply, this is in general how we can find the inductance, the self-inductance and the mutual inductance between the stator and the rotor. So if we know this information, we can start with modeling of three-phase symmetrical induction machine. So let's start with a new topic here, which is the modeling. Of three-phase symmetrical induction machine. And in general, for the induction machine, we have cylindrical stator and cylindrical rotor. So the gap is uniform. So in general, for the induction machine, we have a cylindrical stator and we have a cylindrical rotor. And in this case, the gap is uniform. So this one has uniform gap. And simply this is a type of machine which has a cylindrical stator and cylindrical rotor. Now, in general, the stator has winding that are identical sinusoidal distributed displaced by each other by 120 degree in space. So in general, the stator and also the rotor winding are identical sinusoidally distributed in space displaced by each other by 120 degree. Now, in this case, the machine is called what? If I'm having winding in the stator and the rotor, this type of machine is called what? In general, we have two types of induction machine. Who can answer this one?
Doctor, what was the question?
The question was if I'm having a windings on the stator and the rotor. In this case, this induction machine is called what? The name of this induction machine.
دكتور الوند روتر.
It's a wound rotor type machine. So simply, if I'm having a winding on the rotor, this will called the wound rotor type machine. And if the rotor has no winding, simply if the rotor is bars shorted by a ring, in this case, this type of machine is called what?
Squirrel cage.
It's a squirrel cage, yes. Now this is called the squirrel cage type machine. So without loss of generality, if I'm assuming a Y connected windings, then simply if I'm having this is the first winding, let's say, and if I energize this winding by a voltage, let's say plus minus VAS, a current will flow IS, and an MMF will be generated, and according to the right hand rule, it will pointed toward the X, which we call it AS. All the time, the MMF generated by the AS coil is pointed toward the AS. And this contains an STLs. Now we said that the windings are distributed in the stator and spaced by 120 degree. So simply here I will have the second winding, let's say, and I will assume here I'm having the B. The same thing if I energize the coil by a voltage, VBS, a current will flow, which is IBS, and the MMF will point toward this X according to the right-hand rule. So this will be the BS. Another 120 degree in space. I will have the phase C. And the same if I energize it by a voltage. BCS, a current will flow, which is ICS, and the MMF will pointing toward this one here, CS. Let's fix this one here. Okay, let's assume here is the joint. Good. Now, AS, BS, CS are stationary. AS, BS are stationary all the time. AS is pointing toward this direction. BS is pointing toward this direction, and CS is pointing toward this direction. Now, the rotor, even if I'm having a one type or squirrel cage, equivalently, I can plot a three-phase symmetrical winding displaced by each other by 120 degree in space. So without loss of generality, whatever the rotor type, I can assume three windings, and let's assume that this is the axe for the AR. The BR and the CR. Now, the rotor is rotating by a speed, which is the omega R speed. So simply the angle between here and here is equal to what? This angle.
Theta R.
Theta R, which equal to what? The integration of omega R d tau plus theta R of 0 if I'm having initial angle. Correct? The same thing here, the angle between BS and BR is equal to what? Okay, this is not a perfect plot, but simply you should understand that it will be a theta R. The same thing here.
Theta R.
Is theta R. Yes? Good. Now, if I need to plot an equivalent circuit, let's say, for the stator and the rotor, and before that, let's plot the winding for the rotor. Now, if this one is squirrel cage, I will short those winding. Otherwise, I will connect a supply in the same, similar to the stator case. Now, if I need to plot, let's say, equivalent circuit to represent the coils, I will use RL circuit. So let's assume Y connected circuit, and any winding consists of resistance and inductance. So let's assume that this is the terminal of AS, and here IAS will flow. So this will be plus minus VAS. Let's assume this is the BS. So here IBS, and the voltage from here to here is VBS. Now this one is CS, a current here is ICS, and the voltage here will be VCS. And simply this is, we call it the neutral point. Now, because I'm assuming symmetrical machine, this means that the coils or the windings are identical. So it consists the same resistance. So this will be RS, 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 and the same equivalent terms. So this will be the NS, NS, and NS. Now the same thing I can plot here the rotor circuit. Now, if I'm assuming that this is the AR, this will be IAR, this will be plus minus VAR, RR, NR. The same thing here. If this one's BR, IBR, the plus minus VBR, and this will be the NR, RR. Also here, if this one is CR, this is a current here. I'm assuming that the direction of the current is into the machine. So this will be the ICR, and this will be the VCR, and this will be the N. This is the R resistance, the RR, and this will be the NR. So here I can define IKS is the stator current. Such that K is a counter, can be phase A or B or C. The same thing, IKR is the rotor current. So if you notice here, I'm using S to stand for the stator, and I'm using R to represent, let's say, the rotor. Now the same thing, I can write the VKS as the stator phase voltage. And VKR as the rotor phase voltage. And I will try to use a vector notation. So I will use F, A, B, CS to represent a vector, a Coulomb vector, which is the FAS, FBS, FCS, where F is any function. So it can represent current, it can represent voltage, it can represent flux linkage, and so on. So it can be voltage, current, flux, etc. Now the same thing here, if I need to represent a variable in the rotor circuit, FABCR, which consists of 3 elements, FAR, FBR, and FCR. Sometime I will use the transpose. So I will FABCR, I can represent FAR, FBR, FCR transpose according to the space, let's say. So if this is the case, let's try to write the voltage equation in machine variable. So I need to write the voltage equation in machine variable. Who can help me in finding the voltage equation in machine variable? Who can help me in that? محمد.
دكتور ما اتوقع دكتور نبدا بالماتريكس تاعت لامدا انه نربطها بالريفي
Simply, if you recall in the previous lecture or the first lecture, when we write the voltage equation, we said that it consists of 2 parts. One is due to the Ohm law, IR, and the second one is due to the Faraday law of induction, which is the d by dt of lambda, correct? Yes?
Yeah, okay.
So now I need to write the same thing. I need to write the same thing. Actually, this is the only equation I need to write it for the voltage to represent the machine, or the voltage equation in the machine variable. And after that, I need to find the torque. Then I need to finish the model by writing the swing equation or the mechanical equation of motion, let's say. So simply here, how many circuits I'm having, or how many equations I will have. I need to write 3 for the stator and 3 for what? For the rotor, correct? Yeah? Yes?
Almost.
So the first equation, who will help me with that? Tihal.
المعادلة الأولى للستيتر راح تكون
Yeah.
بدها تكون إنه ال VABC.
So you'll use a vector notation. So okay, VABCS will equal to
RS multiply by ABS
RS IABCS
plus D lambda AB.
D by dt of lambda ABCS. Now RS equal to what?
RS
Mhm.
here already it's equal for all the
So can you give me the shape for RS?
دكتور تكون diagonal.
So it will be RS or diagonal matrix where the diagonal consists of RS. Yeah. So this is a matrix.
Yeah.
This is a vector.
Oh.
Yeah. So this is 3 by 3. So element of R 3 by 3, correct? Now what about the rotor? Who can give me the voltage equation for the rotor circuit? It's very simple. Substitute.
نفس الإشي دكتور
نفس الشيء
بس
دكتور.
بدل R stator
Yeah.
والIce
So
نحط
simply substitute
R
instead of
R.
S, R. Yeah. So you say that VABCR equal RR IABCR plus D by dt of lambda ABCR. Yeah. Sometime instead of D by dt, we are using B, small b, to represent the differentiation. Okay. If you go to the textbook, sometimes he will use small b to indicate for the differentiation. For me, I will use the d by dt. Now, if I need to evaluate the voltage equation, I need to find the flux linkage. Yes. So for that, let's assume a linear magnetic circuit. So for a magnetic linear circuit, which means that lambda can be represented by L multiplied by the current. So the flux linkage can be written as now let's see. Now in general here I need to write lambda, which is the ABCS, and also I need to find lambda, which is the ABCR. Oh. Now the first one, consists of two parts, yeah?
Yes.
Which is, or which are?
LS في IABCS plus الميوتشوال LSR times IABCR.
So simply you are telling me that the flux in the stator consists of two fluxes. One is due to the current in the stator, yeah, and the second term is due to the current in the rotor circuit, correct?
Yes.
Yeah?
Yes.
So simply I can write the first one as lambda ABCS in the due to the stator current plus lambda ABCS due to current flowing in the rotor circuit. What about the lambda ABCR?
The same.
which is
lambda
ABCR بالروتور زائد لمدا ABC
شو اسمه اس بالستيتور صح؟
Yeah, so simply here you can say that it consists of two parts. One due to the current in the rotor itself, which is the lambda A, B, C, R due to the rotor, plus lambda A, B, C, R due to the stator. Yeah. And because I'm assuming a linear max circuit, which means that I can represent lambda as L multiplied by I. So now we can find the lambda ABCS, lambda ABCR in matrix form consists of. So let's see how many currents I'm having. As a vector, I'm having two, which is the I A B C S and I A B C R. Yeah. So the first one here, which is the lambda ABCS, do the stator, which means that if I need to calculate this one, do you remember? This will be LS, which equal LS IS. Yeah. So this will be the LS. What about this one here? This will be what? The inductance as seen between the stator and the rotor. So this will be the LSR. Now, what about here? This one represent what?
LRS.
This term represent this one or this one?
لا تبع الستيتور ده.
Yeah, because here the current is the stator, so this one will be lambda ABC R due to the stator circuit. So this will be equal to what? This will equal to L S R transpose. And this will be what? The self-inductance, which is the L of the rotor, LR. Yes. So now let's try to calculate those elements, LS, LSR, and LR. So the first one, if I need to calculate the LS, so simply if I will use a superposition, I will kill this one here and say that lambda S will equal LS I ABCS, and in this case, this will equal to lambda ABCS of the stator circuit, correct? So lambda ABCS of the stator circuit, which will equal to certain matrix multiplied by the current flowing in the stator, which is I AS, I BS, and I CS. Now the first one here is called the LAAS. Why? Because this one associated with a current flowing in phase A with the flux linkage in the phase A itself. So this can be seen as the self-inductance. Now this one will be the LABS, the inductance between phase A and phase B of the stator, and this one will be the LACS. If this is the case, who can give me this one? I can call it what? L as seen between that and that. Now, this will affect lambda B, correct? The second line is lambda B of S, so this will be the LB. Which current? Due to which current? Phase A current. So this will be LBAS. Well, what about this one?
LBS. EBS.
This will be LBBS, correct? This will be the LBBS, the self-inductance for phase B. What about this one? This will be the LB due to which current? CS. The same thing here. Who can give me this one? I can call it what?
NCAS.
LCAS.
LCAS, yes. So this will be the LCAS. This will be the LCBS. And finally, this will be the LCCS. Now, the diagonal here consists of the self-inductance. So those are the stator self-inductance. And the off-diagonals elements, those are the stator mutual inductance. So those are the stator mutual inductance. Yeah. Now, if I need to calculate the stator self-inductance, and because I'm assuming symmetrical three-phase system, this means that the coils are identical. So this means that LAAS will equal to LBBS will equal to LCCS. Now, any self-inductance consists of two parts. The first one is the leakage inductance, which is the LLS, plus the magnetizing inductance of the stator winding, which is the LMS. So this one we call it the leakage inductance. So the leakage inductance. And this one we call it the magnetizing inductance. Now, if I need to calculate the mutual inductance between the stator winding, so if I need to calculate the stator mutual inductance, which is the LABS, LACS, LBCS, and so on, the off-diagonal element. So this will be the stator mutual inductance. So now let's think about like this one. If I need to find the LABS, which is the mutual inductance between phase A, S, and phase BS. Now the angle between AS and BS is equal to what? This angle equal to what?
120.
Yeah, 120 degree. Yeah. Why? Because I'm having three phase distributed uniformly in circle, which is the 360. So 360 over 3 is what? Is 120. Yeah? If I'm having 5 phase, the angle will be what? If I'm having 5 phases machine or 5 phase machine. In this case, if I need to uniformly distribute the winding, then each phase will be displaced by 360 over 5, which is 72, huh? Yeah. Yeah. Now let's see. If I need to calculate lambda or LABS. So simply here, what? I'm energizing, let's say, coil A by IAS. Then I will try to find lambda here, lambda BS. Then this will equal to what? Lambda BS over IAS. Of course, if I do the opposite thing, it will be the same. If I inject a current in the B and measure lambda in the A, then if I divide, I will find the LBA, which will be the same. Good. Yes. Now simply here.
دكتور معلش. آخر إشي حكيته إنه لو بدي أوجد LBAS حيكون لامدا AS على IBS صح؟
If I need to find this one, huh? Yeah. Now, here, I'm discussing this one, huh? This one actually, if I'm doing the superposition, huh? This actually is lambda A, which equal LABS due to the IBS. So simply I'm injecting current where? I'm injecting current in the B coil. I'm calculating the flux linkage in the AS. Then I can find the LABS, which will equal lambda AS over IBS. Yeah. Now, but because this one is also the same, if I need to calculate this one is actually is what? If I'm doing the superposition, which means that I'm killing all the current except the one that I'm calculating this one here, which is due to this one. Huh? So I'm seeing what here, lambda BS. So for this one, lambda BS is equal to LBAS IAS. So simply LBAS will equal to lambda BS over IAS. But simply I can use either this one or this one, because in the end of the day, LABS is equal to LBAS.
دكتور يعني هي سيمتريك صح الماتريكس؟
Yeah. Yes. Why? Because I'm having cylindrical stator and cylindrical rotor. So the gap is uniform. And the distance or the angle between the phases are fixed 120 degrees. Yes. So if I need to measure the mutual inductance between A and B, or between B and A are the same. Do you remember the start of this lecture?
Yes.
Yeah. In rotating time machine, I'm having stator and I'm having rotor. The stator has self-inductance and mutual inductance. The rotor has self-inductance and mutual inductance. Yeah.
Yes.
Now, for the self-inductance, I can calculate for mutual inductance, for example,
Okay.
between the stator and the rotor. I can have two methods, huh? But also here, this self-inductance has two terms, the leakage inductance and the magnetizing inductance between the stator itself, because here the stator consists of multi-phases. Huh? Three-phase system I'm having, yeah? Three coils. Yes?
Yes.
So simply this means that if I'm having current flowing here, this current will generate what? Flux. This flux not only link NS, but also will link what? The coil for the phase B and the coil for the phase C. The part of the flux that linking only coil A flux is called what? Is called the leakage flux. Huh? It's called the leakage flux. Good. Okay. So if the magnetizing inductance is LMS and I'm having two coils which are distributed uniformly and displaced in space by 120 degrees. So simply if I energize one coil, this will generate MMF, and this MMF is equal to NS multiplied by IS. Yeah. So if I divide it by the magnetizing path, I will get the flux, correct? Do you remember? The MMF equal to what? NI. Yeah. The flux is equal to what? The MMF over the reluctance. Yeah. And lambda is equal to what? N multiplied by the flux. Yeah. So I need to find the projection of that flux where in the direction of the B. The angle between them is equal to what? The angle between the phase A and the phase B is equal to what?
100.
120.
So simply this will equal the LMS cosine the angle in between, which is 1 to 0 degree, and this will be minus 1 over 2 the LMS. Yeah. Now, due to the three-phase balance system, then the angle between BS and CS is also 120 degree, and the angle between CS and BS is also 120 degree. So this means that all the off-diagonal elements here, all the stator mutual inductance will be equal to what? To minus 1 over 2 LMS. So simply here I can write that LABS will equal to LBAS will equal to LBCS will equal to LCBS, which equal LCAS, and this will equal to LACS. And all will equal LMS cosine the angle in between, which is 1 to 0 degree, and this will equal 1 minus 1 over 2 LMS. So simply until now we can calculate the LS. So LS, if I substitute the variable here, this will equal the LS plus LMS minus 1 over 2 LMS minus 1 over 2 LMS minus 1 over 2 the LMS, the self-inductance, which is the LS plus LMS minus 1 over 2 the LMS. The same thing, minus 1 over 2 LMS minus 1 over 2 LMS, and finally here the self-inductance, which is the LS plus LMS. Now L ms is equal ns square over the reluctance, the magnetizing path Rm of the magnetizing path, let's say. Now, until here, we found the self-inductance of the stator circuit. Now, what about the self-inductance for the rotor circuit? Now, which is the LR equal to 1. Now, let's see. Now, if this is the AS and this is the BS and this is the CS, and let's assume that this is the AR and the rotor is rotating by the rotor speed omega r, let's say. And the angle between here and here is theta r. Now, although the rotor is rotating, the angle between AR and BR are fixed or variable?
Fixed.
Fixed, which equal to what? 120 degree. And the angle between BR and CR is what? Is also fixed, equal 120 degree. And the angle between CR and AR is also fixed, which 120 degree. So simply, this means that, and because of having cylindrical rotor, this will be LR will have almost the shape, or will have the same shape of the LS, except that S will go to where? To the R. So simply here, I can write LR, which will equal to LR plus LMR minus 1 over 2 LMR minus 1 over 2 the LMR minus 1 over 2 LMR LLR plus LMR minus 1 over 2 the LMR minus 1 over 2 the LMR minus 1 over 2 the LMR, and finally here I'm having the LLR plus the LMR. Yes, so it's easy to write the rotor self-inductance, and simply we calculate the LMR as a function of LMS, it will hold NR over NS square LMS. Now, in order to finish the model, I need to find the mutual inductance between the rotor and the stator circuit. So in order to finish calculating the inductance, I need to find the mutual inductance between the stator and the rotor circuit. So here, now let's replot the axis. This is AS, this is the BS, and this is the CS. And let's assume that here is the AR, here is the BR, and here is the CR. And we are assuming that the rotor is rotating by omega r, so this will be theta r. So here I need to calculate the lambda ABCS due to the rotor, which will equal now the current here is the rotor, so IAR, IBR, and ICR. So the first one here I can call it is the inductance LAS AR. The second one is the LAS BR. The third one is LAS CR. So this inductance I can call it what? According to this written, this will be what? LBS AR. What about this one? Who can help me with that?
دكتور LBS BR.
BR.
It will be the LBS BR. What about this one?
LBSCR.
LBS CR.
So LBS CR. So simply it will be a straightforward in order to continue with LCS AR, LCS BR, LCS CR, correct? Yeah. So simply the first one, which is the inductance as seen between what and what? This one.
Between AS و AR.
So the angle between AS and AR is equal to what?
Theta R.
Theta R. Now what about the angle between BS and BR?
The same thing,
Theta
Theta
R.
R.
What about the angle between CS and CR?
The same thing, Doctor, Theta R.
So simply this means that LAS AR will equal LBS BR will equal LCS CR, yeah? Yes? So simply this means that LAS AR will equal LBS BR will equal LCS CR, which will equal. Now I'm having, let's say, inductance between LSR, then I need to project according to the angle, so this will be cosine theta R. Yes? Good. Now let's see. What about this one? The angle between LASBR is equal to what?
120 plus theta R.
Yeah. So this is the angle, yeah, which is the 2 pi over 3 plus theta R, or in degree it will be 120 degree plus theta R. Now, what about the angle between BS-CR? BS-CR. This one.
نفس يا دكتور 2 pi over 3 plus theta R.
So this would be 2 pi over 3 plus theta R. And what about CSAR? CSAR.
The same thing, yeah.
2
Theta
pi
R plus 2
over
pi
3 plus
over 3.
theta R. So this will be the LSAR, this one, huh? Correct? So simply this means that LAS BR will equal LBS CR, which will equal LCS AR, which will equal the mutual inductance is L between the rotor and stator as a maximum value is LSR, then cosine, I will project it by cosine the angle, which is equal to theta R plus 2 pi over 3. Now, what about the remaining inductance? Let's assume this one. I will start here. ASCR, the angle between AS and CR. This angle equal to what?
120 minus 2 pi over 3. عفوا 120 minus theta r.
So 2 pi over 3 minus theta r. Yeah? Yes? What about BS AR? BS AR. This angle equal to what? It will be the same, huh? 2 pi over 3 minus theta r. Finally, LSCR. LSPR, huh? LSCBR, which is this one, huh? And this angle is also equal to what? 2 pi over 3 minus theta r. Okay? So simply, I can write LASCR will equal to LBSAR, which will equal to LCSBR, which will equal to LSR cosine theta r minus 2 pi over 3. And remember, cosine of minus theta is equal to cosine of theta. Huh? Good. So we found, let's say, the mutual inductance between the stator and the rotor. In matrix form, I can write it as LSR will equal to, if I need to write this one in terms of the magnetizing inductance LMS, then those will equal to NR over NS LM, the mutual inductance. So simply I can write it as NR over NS LM, and here I'm having cosine theta r, cosine theta r plus 2 pi over 3 cosine theta r minus 2 pi over 3. This will be the cosine theta r minus 2 pi over 3. This will be cosine theta r, and this will be the cosine theta r plus 2 pi over 3. This will be the cosine theta r plus 2 pi over 3, and this will be the cosine theta r minus 2 pi over 3, and finally here I'm having cosine theta r. Now let's do some observation. If you remember, LS and LR. LS and LR are constant or time varying. The self-inductance of the stator and the self-inductance of the rotor. Are those matrices time varying or constant?
Constant.
Depend only in the geometry, yeah? Depend only on the geometry. So this one and this one is constant. Now, what about the mutual inductance between the stator and the rotor, which is the LSR? This inductance, is it constant or time varying?
بيعتمد على الإرجاب دكتور إذا كان salient or non-salient.
No. Now, here, this one is a function of theta r.
Yes.
So it's time varying, correct?
Yes.
Yeah? It's time varying. And remember, without this one time varying, I cannot generate a torque. Yeah? Because in the end of the day, I need the inductance to be what? To be a variable of a time, huh? Or time varying in order to generate a torque. Now, if I have a salient, even if the gap or even if I'm having a single excitation system, one coil, I can generate a self torque or reluctance torque. But here, because I'm having cylindrical rotor, and if we still remember when we discussed a cylindrical rotor, we said that single excitation cannot generate a torque because the torque will equal to 0. If I need to generate a torque, I need to add more excitation, and simply this is the polyphase system, which means that I'm having more excitation. I'm having here 3-phase system on the stator and 3-phase system on the rotor, which make the mutual inductance time varying function of theta r, function of the rotor position. So in this case, I can, or the machine has a starting torque or has a well defined torque, let's say. Yeah. Yes. Until here, do you have any question? Now, the last thing I need to do is to refer the rotor variables to the stator side. And in general, why we are interested in the stator side, because the stator side is the actual side where we impose this, the voltage, and where we can measure the current. In general, the rotor, if the rotor is squirrel cage, actually, I cannot measure the current. It's bars, short bar the ring. So logically, all the time we are doing or referring the rotor circuit to the stator circuit. So if we refer the rotor variables to the stator side, and we will use dash to represent the referring. So simply this will be the IABCR dash, which according to the number of turns in R over NS, IABCR. And as we said before, any transformation, any change of variable must preserve the power, which means that IV must equal I dash V dash. So in this case, VABCR dash will equal to NS over NR VABCR. So we only need to refer the rotor voltage equation, which, if we recall, it was VABCR equal to RR IABCR plus d by dt of lambda ABCR. So if we multiply the first equation by NS over NR, the two sides must be multiplied. So the first one here I would get is the VABCR dash, this one, which will equal NS NR RR. Now instead of IABCR, I can write it in terms of dash. So IABCR equal NS over NR IABCR dash. So simply here I can put, instead of this one, NS over NR IABCR dash. So this will be plus. Now the flux linkage is following the voltage, so this will be d by dt of lambda ABCR dash. Yeah. Now this one is equal to RR dash, and the flux linkage referring to the stator can be written as lambda ABCS, lambda ABCR dash, IABCS, IABCR dash, and this will be the LS, this will be the LR dash, sorry, this will be the LSR dash, this will be the LSR dash transpose, and this will be the LR dash. This is the voltage equation referred to the stator winding. Now LR dash will equal to NR over NS. This will be the NS over NR square LR, and the LR dash will equal also NS over NR squared LR, and LSR dash, which will equal NS over NR LSR. So this will equal to, if you multiply this one, then this factor will cancel the NR over NS, and I will end up with LMS multiplied by the cosine theta, cosine theta 1, let's say, cosine theta 2, cosine theta 1, cosine theta, cosine theta 2, cosine theta 1, oh, this one 2, cosine theta 1, and here I'm having the cosine theta 1, cosine theta 2, and cosine theta, and I will define now theta 1 to be equal theta r plus 2 pi over 3, and theta 2 to be theta r minus 2 pi over 3. So this will be the voltage equation.